In what situation would you prefer coordinate descent over gradient descent? So coordinate descent and gradient descent are two optimization algorithms commonly used to minimize the cost or objective function in machine learning and optimization problems. And coordinate descent is a simple optimization algorithm that updates the parameter values by optimizing one coordinate at a time while keeping other coordinates fixed. In contrast, gradient descent updates all parameter values simultaneously in the direction of the negative gradient of the objective function. So here are some situations where coordinate descent might be preferred over gradient descent. First, when the objective function is separable. If the objective function can be expressed as a sum of separate functions where each function depends only on one or few coordinates, then coordinate descent can be a more efficient algorithm compared to gradient descent. In such cases, coordinate descent can update the coordinates independently and in parallel, which can speed up convergence. Second is sparse features. When the input features have a sparse representation, that is a high percentage of zeros, coordinate descent can be more efficient than gradient descent. This is because only a small number of coordinates need to be updated in each iteration, resulting in much faster convergence. For example, in lasso regression, which introduced the L1 penalty to induce sparsity, coordinate descent is a popular choice. Next one is when the objective function is non-differentiable. So if the objective function is non-differentiable, such as in the case of L1 regularization, then gradient descent may not be used because the minimization will not be guaranteed in that situation. So in those kind of situation, coordinate descent can still be applied as it only requires subgradients of the objective function. Next, when the dimensionality of the problem is high. If the dimensionality of the problem is high, then computing the gradient for all parameters can be computationally superb expensive. In such cases, coordinate descent can be more efficient as it only requires computing the partial derivatives with respect to one or a few parameters at a time. Next reason, when the objective function is not smooth. If the objective function is not smooth or has discontinuities, then gradient descent can get stuck in local minima or oscillate around the optimal solution. In such cases, coordinate descent can be more robust as it updates the parameters in a sequential manner and can avoid getting stuck in a local minima. Another situation to use coordinate descent when input features are highly correlated. Gradient descent in those situations may suffer from slow convergence due to the so-called zigzagging effect. In this situation, coordinate descent can be more effective as it updates one features at a time, avoiding the zigzagging issue. So now let's think of an example illustrating the preference for coordinate descent with lasso regression. Consider a linear regression problem with a large number of features, many of which are not relevant to the target variable. Using lasso regression in this situation, which will add an L1 penalty term to the objective function, can help identify the important features and set the irrelevant ones to 0. In this case, coordinate descent is preferred over gradient descent because the L1 penalty term makes the objective function separable, allowing for efficient computation with coordinate descent. Then the sparsity of the solution favors coordinate descent as well, as only a small number of coordinates need to be updated in each iteration. And the warm start capability of coordinate descent can be leveraged for model selection here, such as tuning the regularization parameter in lasso regression.